Hello, welcome to ME 510, Economics and Policy of Engineered Energy Systems. This is part two of our two-part module on the economics of oil, and we'll talk about extraction and production. When you look at extraction and production of oil, one key figure that is useful to track is the number of oil rigs that are available in the region. What you see in this slide are the numbers of oil rigs that are found on the left in North America and rig count, outside of North America on the left and rig count in North America on the right. You can see here that in the 1980s, North America had a very high rig count, and that rig count declined throughout the 80s and 90s, remained steady. And then in recent years, we've seen a resurgence in the number of rigs being installed in North America, due mostly due to the fracking revolution, if you may. And a lot of these rigs are located near shale gas regions, as we'll see in later presentations. Around the world, what we've seen is that for many of these places, the number of rigs has remained either steady, stable, as in the case of Africa at the bottom, or has followed a similar pattern where it either declined initially, stabilized, and then eventually increased due to technology and at some point rising economic prices. As you can see, this graph only goes to about 2008 or 9, and so it doesn't really capture some of the recent declines that we've seen due to the significant drop in the price of oil. So what are the things that you have to consider when you look for oil and try to extract oil? The first question is how big are your reserves? And if you read through the U.S. Oil policy timeline, you will know that reserve estimates are a major area of contention, particularly with countries that are part of OPEC, the Organization of Petroleum Exporting Countries. Members of OPEC are often allowed to produce a certain amount of oil per year, depending on the reserves that they have. And so in order to produce more oil or generate more income for a given year, they can often try to inflate their reserves. But let's look at the methods. So the first method described here is the volumetric method. It's based on raw engineering and geological data. It gives you a recoverable oil estimate using some recovery factors and essentially engineering background and knowledge about the wells. Now, another method is a material balance. So if you're able to measure how much you're producing and how much is available, then you can use a formula to calculate how much may be in the total reserve. A more common one is the pressure decline. This is used mostly in non-associated and associated gas reservoirs. In this case, basically you're measuring how fast the pressure is changing at the exit, and that will tell you more or less how much gas is available in that deposit. For crude oil, a similar measurement is the decline curve. It's most useful at the later stages of a reservoir life because at the later stages, as the deposit gets depleted, you can see more drastic changes in the rate at which the oil is extracted. Okay? And you have more past production data that you can extrapolate as well. Now with more computational resources, you can actually try to design reservoir simulations, and you can try to use the simulation computational tools to estimate how much oil is available. If you have pressure and production data, again, you can calibrate these reservoirs to better predict how much oil and gas they have. The final and least accurate method is to use the nominal approach, and this is where you have an engineer with years or decades of experience. They can tell you based on inferences how much oil will be available in a given well. It's fairly quick to do. There are people who are really well known for doing this, but it is in fact the least accurate method. Now, once you start extracting oil, one thing that you have to worry about is cash flow. In recent years, we've heard about shale gas companies having trouble with cash flow, particularly with when the financial markets had some recessions and crashes in recent years. And this figure sort of gives you an idea why the finances are important. So if you look at a typical revenue for an oil rig, if you start from year one, you're not producing oil. You've done some initial investment that's not reflected in this graph, but you're starting to incur some costs. And so the first 3 to 4 years, you're paying your labor, you're paying your leases for the land, your contracts, and so you are going to be negative for several years. When you take into account the amount of interest that you have to pay to your original investors, you can see depending on how much they're demanding, 0% or 10% rate of return or 44% rate of return, you might end up at different levels of negative income. By year 5 in this drawing, it could be earlier or later, but 3 to 5 years is typical. By year 5, you start generating some profits. You're still not making enough to make up for the initial investment, but in principle, you're starting to produce enough oil or gas to generate some income. By year 6, your resource or your rig should be producing a maximum capacity. This is when the rig has been completed and the reservoir is still relatively full, at least at its maximum that you found it. And so you're getting the maximum output that you can get. Now, shale gas rigs are famous for having rapid declines in the amount of gas that they produce right away. And so this picture here might be representative of a shale gas reservoir. And you see that from year 6 to year 7, you have an almost 50% or greater than 50% decline in production. And that decline continues, although it decreases the rate at which it decreases into year 10 or further. The lines that are shown here representing the rate of return, 44% in this particular example is the maximum rate of return that they could get while still making a profit at the end of the life of the project in 10 years. If the investors only require a 10% rate of return, which is what the market usually demands, or at least if you're competing with the stock market, then you might have a surplus amount of revenue towards the end of your project. If you want to look at the zero rate of return, which is the break even for the initial investment, you can see that you do end up with several more million pounds in additional revenue that could go to laborers or equity or other agents. These interest rate values were chosen, I believe, because 44% is the typical rate of return for a successful, an average oil rig. 10% is a typical investment that any investor would like to see on a project. And a 3 to 5 year payback period is what it's called, is also a very typical range for investors that are in this type of energy industry. Now, when you're trying to categorize different reservoirs, you can put them into this McKelvey diagram in order to understand, one, what is the economic feasibility? How much money do you expect to get out of it, or do you expect to get any at all? And on the other axis, geological uncertainty. Are there actually reserves there? And do we actually know with good confidence how much is available? What the McKelvey diagram does is it puts them into 4 quadrants, 4 key quadrants. These are the identified resources. You can have either proven resources or inferred resources. And among proven resources, you can have economically recoverable resources. And those are the ones that you want to develop. And you can have uneconomic resources and reserves, which may have been proven, but they may be difficult to develop with the given technology and financial situation. When you have inferred uneconomic reserves, these are reserves that you may have not explored enough to determine to prove them, but you may already know that even if you prove them, they are going to be uneconomic. Now, even though we've explored significant parts of the planet, there are, of course, a large number of potential undiscovered resources that are in the McKelvey diagram either hypothetical or speculative, and this means that either we know they should be there because the formation, or other factors suggest that it should be there. Speculative could be simply a country believing that they should have oil due to some historical finding or other non-verified reason. Once you extract the oil, well, not all oils are the same. And what you're seeing in this graph is a picture from the Energy Information Administration Agency. And what it's trying to show are the different types of oils that are marketed around the world. The two key characteristics that you need to consider when comparing oil are the sulfur content and the API gravity, American Petroleum Institute gravity. It's a measure essentially of the crude oil density. You can see the equation here at the bottom. In terms of the API gravity, crude oils are categorized as either light or heavy. And in terms of the sulfur content, they're either sour or sweet. In principle, you want to get as much sweet oil as possible because the sweet oil has a very low sulfur content. And what that means is that you will have to do less desulfurization, particularly if you're trying to sell the oil in the European and US markets where sulfur is heavily regulated. And so those oils will have less processing required. You can see that United States has a fairly amount of sweet oil, or at least the oil that comes from the West Texas Intermediate region and some other parts of the US are relatively sweet and relatively light. However, if you go to places like Mexico or Saudi Arabia, you're finding heavy oils with a lot of sulfur. Here's another view looking at more specifically essentially the value of the different crudes and where they come from. And so to the top left is a high value crude. What that would mean is it has to have a light density and it has to be sweet. So you can see that West Texas Intermediate, WTI, is considered one of the best crude oils in the world because it has both a light gravity and a relatively low sulfur content. On the opposite end, you have the Venezuelan Pilon oil, which has a relatively high density and very high sulfur content. If you want to look at the relative percents of crude oils that are known around the world and where they stand in terms of API and sulfur, this picture tries to show what that is. So you can see the Middle East has some of the largest known reserves of oil. However, their oils are known for having a high API gravity and high sulfur content. North America, as we saw earlier, has some very valuable oil. However, the amounts that are known in that sense are much smaller. If you look at the expected changes in quality by 2020, because we're moving towards these shale gas formations, they tend to have a little bit more sulfur. So North America is expected to have a decrease in quality in terms of the oil that it exports. Africa and Latin America expect to have an improvement in crude quality. Middle East, in the same vein as North America, a decrease in quality by 2020. Now, why do we care about these different types of oils? What can we get out of them? So if you look at the characteristics of the oil, we already talked about the API gravity and the sulfur content, but there's also a certain amount of demand. As I already mentioned, countries that are trying to decrease their sulfur emissions are not going to want high sulfur containing oils, and so they'll have a lower demand in those regions. Light sweet has about 35% of the world demand, medium sour has about 50%, and then heavy oils have a very low demand. But they're also the least expensive. In terms of the yields that you get out of this, you can see a breakdown here. On the gray side are the refinery gases, this is just natural gas. Then you have the gasoline at different rates, followed by distillate, which includes jet fuel, diesel, and heating oil. And then 9% heavy fuel oil and other in U.S. refinery production. Okay? And here we're only looking at the commodity products, the ones that have high volume products. A barrel of oil actually produces a lot more than just gasoline, diesel, and transportation fuels. And sometimes those other products, those chemicals, have such a high value that that's where the bulk of the revenue comes from. This concludes part two of our oil economics presentation. I encourage you to read the textbook for some more information, and we'll continue on to module three.